All right, welcome to our second part of the Chapter 8 discussion here for one of our recorded lectures. So what we're going to be talking about today is mainly focusing on Lewis dot structures. How do we draw them? What are some of the finer details we want to pay more attention to with things like formal charge and resonance, so we know what those terms are and how to recognize when those things are going to show up in molecules. And then at the end, we should have a little bit of time to talk about bond dissociation energies again with covalent compounds. But now, having talked about Lewis structures, one of the things we can do with that is use those bond dissociation energies to find a change in enthalpy for a reaction. So those are the two main focuses we're going to take a look at today. And for the Lewis structures part, it is going to take a while. You've probably seen some of this from the lab material already. So some of this will look familiar, and some of the slides might even look very similar since I did make that video also. But bear with it. I'm going to have some other examples that are different as we kind of get towards the end of this part. And then we'll have our discussion, like I said, on the bond energies. So as a starting point, Lewis dot structures, kind of what they exactly are. They're kind of a visual representation of all of the valence electrons of all the atoms in a molecule. We represent those electrons by basically just dots in our structures. So if it's like a lone pair of electrons, we'll draw it as basically like two dots to represent the pair of electrons in what we call a lone pair. Or we can have bonds, which are typically going to be indicated by single lines between two atoms, and the single line will represent two electrons being shared between those two atoms. And again, just kind of to show that in an image down here. Here we see we have two different fluorine atoms. Fluorine has 7 valence electrons normally, so that's the 7 dots that we see around each fluorine. And we do usually break things into kind of semi-quadrants when we draw out those electrons on individual atoms. And so that's why you kind of see the orientation like this. That's pretty consistent in terms of how we usually organize things. And then these 2 electrons here that are kind of the unpaired electrons on the atom by itself, then those are the electrons that are going to end up being shared to make that covalent bond. And instead of drawing it like a pair here, usually like what's stated up here, you're going to have a single line that'll connect these 2 atoms instead. Now, the nice thing about drawing Lewis structures, it is a really systematic process, meaning that you're going to do the same steps basically every time for every example, and you should never have to do anything different. As you get better at drawing them and you've just drawn a lot of Lewis structures and you recognize a lot of the patterns and things like that, then you can maybe get away with skipping a couple of these steps, or just kind of you almost have like an intuition of what things are likely to look like. But that's something, if you've never drawn Lewis structures before or haven't looked at these in a long time, better off just following all the steps and being very systematic about it right now, because these steps should always get you to the correct answer. The only thing that can sometimes be tricky is maybe the very last part about checking for formal charge and resonance, but hopefully we'll detail that in a handful of examples today that'll make that process a little easier. Now, starting point, these first 2 steps for drawing Lewis structures, you can probably do them kind of in any order, but I usually like to just look at my molecule and figure out how many total valence electrons do I have to work with. And so you look at every atom in the molecule, figure out how many valence electrons there are. Also pay attention to charges. Right? If you have a positive ion, then you're going to basically subtract that number of electrons from your total valence electron count. Negative charge, the opposite, you'll add electrons to your total electron count. The second step, what we're going to do is draw what we call a skeletal structure. It's kind of just like a starting structure of everything. And the biggest, probably most important part of this is picking a central atom. And in general, we say that the least electronegative non-hydrogen element is typically going to be our central atom. And if that's not the case, we will tell you basically what the central atom is going to be, but otherwise this will always be the case for any formula that you're just given. Now, you may be thinking it's like, oh, well, I have to pick out which is the least electronegative all the time. It's actually easier than that for most examples that we see, because when we write chemical formulas, the first element listed usually is the least electronegative atom. And so that actually will help make this process quite a bit easier as we start getting into our examples. All right, once we have our skeletal structure with just single bonds kind of connecting everything to that one central atom, then we're going to fill the octets of all of the outer atoms with lone pairs. The only time you wouldn't give a full octet to something is if that's on the outside of the molecule, is if that outer atom is hydrogen. If the outer atom is hydrogen, it's going to make its one bond and that's it. Hydrogen doesn't want an octet because it only needs to fill an s orbital. It doesn't have any p orbitals in that first energy level to have to worry about. And so hydrogen basically makes its one bond, and it counts 2 electrons from that one bond, and that's all it wants. It doesn't want any more. Once we've added those octets then to anything that's not hydrogen on the outside, if there are any electrons left over, and this is where counting the total valence electrons at the beginning is kind of important, if there are electrons left over, what we're going to do is add them to the central atom as lone pairs. And this will always be the case. This is probably one of the places where I see the most mistakes get made. People get to this point, they fill out the outer octets, they have leftover electrons, and they just start making multiple bonds for no real reason, or there's no necessity for the multiple bonds. You only make multiple bonds if you don't have enough electrons for the central atom and you don't have any left that you can add anywhere else. If you have leftover electrons after filling the outer octets, the leftover electrons are always lone pairs in the central atom, every single time. There's zero exceptions to that. But it is a very common mistake that I see in people when they're drawing these structures for the first time. All right, once we've gotten to that point, then we're basically going to look at our central atom and do kind of a quick check, because it's possible we're already done, but in a lot of cases we might not be. And so that check is we're going to look at our central atom, and we want to know, does that central atom have an octet? And what we mean by that is we want to see 8 electrons around the central atom, where each lone pair counts as 2 electrons, and each bond also counts as 2 electrons in terms of our counting for that total. If the central atom is short of an octet, at this point, then we're going to want to try and make multiple bonds. And I'll kind of demonstrate how that process will work. It basically involves removing a lone pair from one of the outer atoms to then make that double bond, or that multiple bond, to the central atom instead. And like I said, we'll have some examples that'll demonstrate this, and I think that will make it very clear what happens in these cases. But again, multiple bonds only going to happen if that central atom is short of electrons and you don't have any left to put on it for lone pairs. Now, the very last part of this is to check for resonance and also formal charge. And these are both things that we're going to be talking about a little bit more as we go. Resonance I'll talk about a little bit later on once we get to an example that has it. It's kind of weird to talk about until we actually see an example that contains resonance for us to really discuss and go over. Formal charge, on the other hand, is something that we can talk a little bit more about. So I'm going to talk about what formal charge is and how we calculate it, and then I'm going to jump into just doing examples. We'll have a handful that we're going to go through. So formal charge, before we get to those examples. So really what this is, it's kind of the charge an atom thinks it has in a Lewis structure, based on kind of all of the things that are attached to it and how it's bonding to everything else. And in terms of how do we really figure this out, there is an actual just systematic equation or formula that we can use. And that's that our formal charge is going to be the number of valence electrons that an atom would normally have, minus the number of bonds that atom is making, minus the total electrons in lone pairs for that atom. And depending on what reference you look at, you might see this middle part instead of number of bonds. They might say like 1/2 the number of bonding electrons. But remember, each bond has 2 electrons, so half of that is just 1. So half the number of bonding electrons and the number of bonds are the same thing. The formal charge really is built all around like looking at electrons. But in terms of just calculating it, like usually for me anyway, it's easier to count number of bonds. But some people may not want you to think about it that way. Like they want, it's just, again, 2 different ways of looking at kind of the same thing. So if you see references that do show like, half the number of bonding electrons, that is what that number of bonds is representing in this case. So to give a quick example, if we have an oxygen atom that happens to be making 2 bonds and has 2 lone pairs, then the formal charge is going to be 0. And the way that works is oxygen, if we look in the periodic table for what it has normally, oxygen does have 6 valence electrons. That's because it's in group 16. And then if we subtract our 2 bonds that the oxygen is making from the description, and we subtract 4 total electrons from the lone pairs, right? Because each lone pair should have 2 electrons in it. So all the electrons in those 2 lone pairs is 4 total. So 6 minus 2 minus 4 is 0. And the goal really of formal charge is to have as many atoms with 0 formal charge as possible. That should be the most stable structure that we can try and put together for any Lewis dot structure. So that's kind of the goal. So we want to see 0 for a formal charge as often as possible. And because of that, you'll actually see a lot of patterns that come out of this. So this description of 2 bonds and 2 lone pairs for oxygen being a 0 formal charge, that means in most structures that we see for oxygen, it's probably going to have 2 bonds and 2 lone pairs, because that's what gives it a 0 formal charge. There will be some exceptions to that, but for the most part, this is what we'll see for oxygen most of the time, unless it is going to be like an ion of some kind where the oxygen has a formal charge on it. Excuse me. All right. Now, one other thing, and this is going to be important as we get into looking at polyatomic ions and drawing Lewis structures for them as well. If you add up all the formal charges of all the atoms in a molecule, they need to add up to the total charge of that molecule. So if you have a polyatomic ion, that has like something like carbonate is an example we'll eventually see later. CO3 2 minus. If you add up all your formal charges, it needs to add up to -2. And that is something that you should see take place. Now that said, +2 and -2 formal charges on single atoms are usually not very stable. And so usually you want to avoid that if at all possible. So a lot of times if you have like a +2 or a -2 overall charge on a molecule, you'll probably have a couple negative or a couple positive formal charges spread throughout the structure. Now, I do say here, and this is something that I mentioned kind of in the Lewis dot structure, like steps as well, like look for formal charge, but really when I say look for formal charge, you want to minimize formal charge whenever possible. And I will show some examples today of exactly what I mean by this, because sometimes you might be able to draw multiple possible Lewis structures that all obey octet rules, but the structures may not be equal to each other because the formal charges are different. And so how we know what the best structure is we pick the structure that has the lowest formal charges in basically throughout the structure. And again, like I said, I'll show some examples that'll kind of help us with this. We'll look at an example of CO2 and how we know what the structure of CO2 is by comparing formal charges because we have options in how we make multiple bonds in that molecule. I'll also show an example towards the very end of sulfate, and we'll see how really formal charge will actually cause some atoms to take on expanded octets if they're able in order to help minimize formal charge. And so we will take a look at that as well. Now, next thing I want to get into, we'll just actually go through examples of this process. So the first few of these I'm going to do just kind of in the slides because I have them there. Just kind of a quick reference. If you've seen, and probably a couple of these are the same ones you've seen for lab, that's fine. If you want to skip to where I'm on the whiteboard, I'll have some new examples that are a little bit different. That's totally fine and up to you. But I'm going to go through step by step on these. I'll also go step by step in the ones after on the whiteboard. But to just kind of review this process, for those that haven't seen the pre-lab video for lab 11, drawing the Lewis structure for water, generally first step, looking for how many valence electrons we have. So we want to look at a periodic table. And I'm going to back out here for just a second so we can look at a periodic table as we do this. And so here we have a periodic table. We're looking at water, so we have oxygen, which we're counting across 1, 2, 3, 4, 5, 6, group 16 right here. There's oxygen, should have 6 valence electrons. We have hydrogen that has 1 each. So 2 for each of the 2 hydrogen, or 1 for, on each hydrogen, 2 of them is 2 total, plus the 6 on the oxygen is 8 total valence electrons. So then the rest of our steps here, once we have our electrons, then we're going to draw our skeletal structure. Now, normally the first element in the formula is the central atom, but hydrogen actually can never be the central atom. Hydrogen is not capable of making more than 1 bond in anything for any of these covalent structures. So as a result of that, whatever elements after the hydrogen is usually in the central atom, which in this case will be the oxygen. So oxygen will be the central atom. Both hydrogens are going to be attached with a single bond. The third step is filling the outer octets. But in this case, we said that the only element you don't fill an octet for in the outer atoms is hydrogen, because it only wants the 2 electrons that come in a single bond anyway. So really, all the outer octets are essentially full here because hydrogen doesn't want any octets. And then the last part of this is we're going to look at how many electrons we started out with, which in this case was 8. We look in the structure, and we've used 2 in this bond and 2 in this bond, so that's a total of 4. That means there's 4 electrons that are still left to be used in the structure, which means those 4 electrons are going to go on the oxygen as lone pairs, right? And so we're going to see the 2 lone pairs added to the oxygen, and there we have now a Lewis structure for water. We still want to check kind of the last couple steps, which were check for like an octet on the central atom, check for formal charge, check for resonance. So if we look at the central oxygen right here, so oxygen has 1, 2, 3, 4, 5, 6, right? 2 electrons in each bond, and then 7, 8. Oxygen does have an octet, so that's good. We don't have to make any multiple bonds here. Formal charge, we said before, oxygen, if it has 2 lone pairs and 2 bonds, that's a 0 formal charge. Well, look what it has here. It has 2 lone pairs and 2 bonds. So that matches up. We have 0 formal charge in the oxygen. Hydrogen, 1 valence electron minus the 1 bond minus 0 lone pairs, also a 0 formal charge, so everything is good here. And there is no resonance. If you don't have any multiple bonds, you never have any resonance. And so we'll eventually, like I said, we'll get to the resonance part of things in just a bit. All right. Look at another example then, carbon tetrachloride. So for CCl4, we want to go through the same general process. Periodic table wise, if we look for carbon, Right, 1, 2, 3, 4. So 4 valence electrons on carbon. Chlorine's over here, it's a halogen. So from carbon, I mean 5, 6, 7. So chlorine should have 7 valence electrons each, which means that now for our chlorine, 4 times 7, since we have 4 chlorines, should be 28, plus the 4 on the carbon is 32 electrons total to get started with. For our skeletal structure, right, carbon's the first element listed, so carbon's the central atom. So our skeletal structure will look something like this. All of our chlorines single bound to the carbon. Step 3 is filling all the outer octets. So we didn't really have to do this in the last example because hydrogen didn't need a full octet, but these chlorines do. And so here we see 3 lone pairs on each of them that we've now added. And then our next step is checking to see what we have left. Right? How many electrons are left? Do we have to add anything? If we add up all of these electrons, and if you're trying to count all of these, sometimes that will take a while. So a quick way to sometimes do it, if everything has an octet on the outside, we have 4 atoms on the outside that each have their own octet. So 4 times 8 is 32. So to draw this picture that we have right now, takes 32 electrons. We started with 32, so there's none left. But the good news is, this carbon in the center already has 2, 4, 6, 8 electrons around it. It already has its octet. Doesn't want any other electrons. If we want to check formal charges, carbon has 4 valence electrons normally. Here we have 4 bonds, no lone pairs, so 4 minus 4 is 0. Chlorine has 7 valence electrons normally. 7 minus 1 bond minus 6 total electrons in our lone pairs there is also 0. So all 0 formal charges. There's no multiple bonds, so there's no resonance to worry about. So this is our complete structure. We have that octet on carbon. Everything looks good here. All right, so now we'll take a look at an example that's going to have a multiple bond in terms of like how do we recognize when that happens and look at how that process works. So for CH2O, we've looked at all these elements already, right? Carbon has 4 valence electrons, each hydrogen has 1, oxygen has 6, right? So 4 plus 2 times 1 plus 6 is 12 valence electrons total. Skeletal structure here, carbon's the first element listed, so we're going to put it as the central atom. So everything goes attached to that central carbon. And in terms of how you draw this, 3 dimensions, for Lewis structures, I personally do not care if you put them in a proper VSEPR geometry orientation because we haven't even really covered VSEPR yet, especially lecture-wise. I usually cover the geometry and the shapes after we've gone over all the Lewis structures. So all I care about in the Lewis structures is just have the right number of bonds and lone pairs on everything. That's what I'm looking for. We'll talk about the 3-dimensional shapes next, and then we'll use, once we've talked about those, then to kind of go further and look at the applications of the shapes for things like polarity. That's kind of where we're heading with all of this. And you'll probably seen some of that from the lab if you watched all the lab videos already, but that's where we're going kind of in lecture as well. We kind of intentionally almost double up in this material between lecture and lab because this stuff is so critical, not just to like the future for like 1212, but also to any chemistry class you take in the future, like organic and beyond. Lewis structures, polarity are topics that you need to understand and really, really have down and be very comfortable with, or else those other classes are going to be much, much harder than they should be. All right, now back to our structure here. Now we have our skeletal structure for this is formaldehyde, the CH2O. Step 3, fill the outer octets. Well, hydrogen doesn't need the outer octets, but oxygen does, right? So oxygen's going to need 3 pairs of electrons, right, to get its octet. So now oxygen has 8. So now we've added all of the octets to the outer atoms that need them. Next step, we're going to go ahead and look at the central atom. Right? If you look at our central atom, carbon here only has 2, 4, 6 total electrons around it. So carbon needs more electrons, but we only had 12 electrons to start. And notice we've used 2, 4, 6, 8, 10, 12. We've used all of them. So this is the situation where we need a multiple bond. The carbon doesn't have an octet, and we don't have any leftover valence electrons from what we started with to give it an octet. So what we end up doing in these cases, we're going to make a multiple bond where we can take a lone pair of electrons off the oxygen and add it to the carbon. And so that's what we're going to do. So here we have a lone pair of electrons. We're going to move it and basically make an additional bond from the oxygen to the carbon. And so now we have a Lewis structure that looks like this. Now, most of the time, if you have 2 lone pairs on an atom, probably you're going to have like a 1 lone pair on each side is probably the more common notation for that. Like if I was drawing it myself, that's probably the way I would draw it as well. So some people are really picky about that. Some are not. I'm not super picky about how exactly you orient or draw your lone pairs, as long as it's very clear how many lone pairs are there. But there are some people that are a little more picky and would like you to see you space things that way. So probably these lone pairs should be like here and here if we were really trying to be technical about how most people will draw them. Now, once we've made that double bond, now we can check again for like our octets or formal charges, things like that. Carbon, like our previous example, carbon's making 4 bonds, so it's going to have a 0 formal charge again. Each hydrogen is 1 bond, so 0 formal charge there. Oxygen, 2 bonds, 2 lone pairs, like the example we saw before with water, also has a 0 formal charge. So all of these have 0 formal charge. We do have a double bond, which means there's maybe a possibility of resonance. But if the double bond is to an atom that is different than all the other outer atoms, then there isn't going to really be any true resonance that we're likely to see in this case. We're going to see resonance in an example in just a second, but in this particular instance, we don't have any. Right. CO2. So now we're going to look at an example where formal charge actually makes a big deal to what the correct final structure is. So still going to go through the same steps we've been doing. So starting process, right? Finding valence electrons, we already know carbon has 4, each oxygen has 6. It's going to give us 16 total. Skeletal structure, carbon's going to go in the middle. Right, for CO2, carbon's the first one listed, so carbon's in the middle, 2 oxygens. We'll fill our outer octets. And if we count our electrons it takes to do this, we have 8 on each oxygen for a total of 16, and we only had 16 to start with. So that means for step 4, our next step, we don't have any leftover electrons to be able to add to our carbon. So carbon gets no lone pairs, but carbon only has 4 electrons total around it. So step 5, trying to count the correct number of electrons for our carbon, we're going to need to make multiple bonds. So if I take 2 electrons off of one of my oxygens, I make a double bond, but I still only have 6 electrons on the carbon. So I'm not actually all the way there yet, even with 1 multiple bond. So what I have to do is actually make an additional multiple bond in this case. And I have 2 options now, and this is where formal charge really starts to matter. Right? I have one option where I can make an additional double bond on the right side and have 2 double bonds, or I could make a third bond on the left side and have a triple bond and a single bond. And there is a way to differentiate which structure is better, right? And so we have two possible options. In terms of how do we know which one is better, we're going to look at these 2 options, and it's really all about formal charge. And so I'm going to go to the next slide where I kind of detail of these 2 which one is actually better, because there is a difference between them. So using our formal charge, if we look at this left structure first, this is the one that has a triple bond and a single bond in it. If we're looking at the left structure, this oxygen on the far left is going to have a +1 formal charge because we'd have 6 valence electrons on oxygen normally, minus the 2 in a lone pair, minus 3 bonds is a +1. Carbon has 4 bonds. That's pretty standard for it. It does have a 0 formal charge, but the other oxygen, if this whole thing was neutral and this oxygen was +1, that means this oxygen needs to be -1 just to balance all the total formal charges. And if we calculate it, that is what it comes out to, right? Oxygen normally has 6 valence electrons. Here we're subtracting 6 lone pairs, and 1 bond will be a -1 formal charge. And so we do have a plus and a -1 formal charge in these oxygens if we draw it this way, but if we draw it with 2 double bonds and calculate formal charges, they're actually all going to be 0, right? Both oxygens will have the 2 bonds and the 2 lone pairs that oxygen normally likes to have, and so that's going to work out very nicely. And the carbon has the 4 bonds again, so everything has 0 formal charge, which means that our better structure is that structure on the right, because it has fewer total formal charges in the molecule. So that right structure with the 2 double bonds is the correct one that we would draw, or the best one that we can draw for CO2. And so this is a good example of how formal charge helps us identify the best possible structures for things. Our goal is always which one has the fewest, basically non-zero formal charges. That's the goal for trying to draw these Lewis structures. Excuse me. All right. So couple more examples from the slides, and then like I said, I'll jump to whiteboard examples also. So one, we're going to take a look at SF6. This is one that's a little bit bigger. So, and we'll kind of refresh ourselves of what it means to have to, or what things are required to have what we call expanded octets. But as a starting point, total number of electrons. So sulfur is right below oxygen on the periodic table, so it is going to have 6 valence electrons. Fluorine is right above chlorine, which we saw earlier in the periodic table. Chlorine had 7 valence electrons, so fluorine also has 7. So we see here 6 fluorines times the 7 for each fluorine. Our grand total here should be 48 valence electrons. Right, so it's a lot of electrons that we're going to have in this structure. But for our skeletal structure, sulfur is listed first, so sulfur in the middle, single bonds to all of our fluorines to get started. And then step 3, filling all those outer octets, it's a lot of dots. And this is a perfect instance of where I said before, if you want to kind of shortcut counting all of your electrons to see if you have any left over to go on the central atom, think about it in terms of numbers of octets rather than trying to count every dot. It might just be faster. We have 6 atoms. Each one has 8 electrons around them, so 6 times 8 is 48. So we've actually used all of our electrons. So sulfur doesn't have any electrons left for lone pairs. And when we go to look at sulfur, sulfur actually has more than 8 electrons. And so this is an instance where we have to kind of stop for a second and think, all right, well, our goal is always 8. That's kind of our magic number. Is it okay to go over that magic number? Like when there was fewer than 8, we made multiple bonds. But what happens if there's more than 8? And it turns out really the only thing we really care about is, can that element actually take on a full go beyond the full octet to take on what we call these expanded octets. And the only real requirement for that is to be in the 3rd row of the periodic table or lower. And if we do look at the periodic table here real quick for sulfur, this is the 3rd row of the periodic table. And what happens is these elements, especially like phosphorus, sulfur, and chlorine in particular, this happens pretty often for, those elements can expand their octets because by being in the 3rd row, if we think back to our quantum numbers previously, you have access to d orbitals in that 3rd energy level, but for like silicon, phosphorus, sulfur, and chlorine, those d orbitals are all empty. And because you have those empty d orbitals, that's what can take on help take on some of these extra electrons. And so now you're able to expand your octet and have more than just that magic number of an 8. And so what we see here for our SF6, this is our final Lewis structure. Sulfur is totally fine having 12 total electrons around it from those 6 bonds. Because it is in the 3rd row or lower, taking an expanded octet, not a big deal. Formal charge-wise, fluorine, like all of our other halogens, like chlorine as well, 1 bond, 3 lone pairs. That's kind of the standard for halogens, especially if they're the outer atom. That'll be their kind of configuration for a 0 formal charge. Sulfur's formal charge. Sulfur has 6 valence electrons. It's making 6 bonds, no lone pairs, so 6 minus 6 is 0. It's also happy, so everything's good. This just is our final structure for SF6. Right. Another one with an expanded octet, we'll take a look at ICl3. Right, so same process. Iodine and chlorine are both halogens, so iodine has 7 valence electrons. Each chlorine has 7, so a total of 28 electrons here. And so we're going to draw connecting all 3 of our chlorines right to the iodine. Iodine being first is the central atom. And so next step, lone pairs. Fill all of our lone pairs on the chlorines. And once we've done that and filled all our chlorine lone pairs, our next step is to look at how many electrons have we used. Right, we started with 28. Initially we had, in this current skeletal structure we have 24, right, 8 on each chlorine. And so 28 minus 24, we have 4 left over, which means all those leftover electrons always go on the central atom, even if it gives the central atom an expanded octet. Right, so in this case we add those extra electrons to iodine. That does mean iodine has 10 total electrons here around it, right? 2, 4, 6, 8, 10. But if we look at the periodic table real quick again, iodine's way down in the 5th row. So that's completely fine, not a big deal that iodine is that low in the periodic table. Not that big a deal that iodine's expanded its octet. It's plenty low in the periodic table to take an expanded octet and have those d orbitals to help out. So this, and then the last piece, formal charge-wise, just to kind of, again, always check. Each chlorine, 3 lone pairs and 1 bond, so 7 minus 1 minus 6 is 0. Iodine, also a halogen, so 7 valence electrons, minus 3 bonds, and then minus 4 in lone pairs is also still 0. So all 0 formal charges, again, a neutral compound, so all of that works out. So that should be our best Lewis structure for ICl3. Right. One last example before I kind of go to the whiteboard for some of these examples to kind of show you how I kind of draw these two. And the last example we're going to take a look at is ozone. So we have a way to introduce and talk about resonance a little bit as well. So for ozone, we're still going to go through the process as normal. We have 3 oxygens. They each have 6 valence electrons, so that's 18 total. So we see here we're going to have just 1 oxygen. We just pick one to be the middle, both oxygens attached to it. Fill the outer octets. That's going to take up 8 electrons on each outer oxygen, so 16 total. Started with 18. That means we get 1 lone pair in the central oxygen. Now, the only issue with this is when we look at our central oxygen, we only have 6 electrons, right? Which means we do need a multiple bond, but how do we know which of the 2 outer atoms to pull a lone pair from? Well, I can make a double bond on the left, but I don't really have any way of knowing that I should make it over here versus over here. And the reality of it is, this is really what resonance is. When you have options of where to add your multiple bond to outer atoms that are the same, and you're going to end up with basically the same formal charges, whichever way you organize it, that is really what it means to have what we call this resonance in a Lewis structure. So here we see these two versions of this structure. They're effectively equal, right? Neither one is better than the other. The formal charges are going to be the same in each of them, right? It's going to turn out here's an oxygen with 2 lone pairs and 2 bonds, so that'll be a 0 formal charge. There's an oxygen in the other one also that's going to have a 0 formal charge. The central oxygen in both versions of these structures is going to have a +1 formal charge, right? 6 valence electrons minus 2 in a lone pair minus 3 bonds is going to be a +1. Same thing over here, right? Looks the same. And then this oxygen on each of these is going to have a -1 formal charge. And so they have the same formal charges, like total everywhere in the molecule, so neither one is better. And so when we have these equal kind of options for drawing our Lewis structures, this is what we call then resonance. And we see typically what we'll do for our resonance structures, we'll draw each of them and use these little two-way arrows between them to indicate the resonance being present. Now, I do want to talk about what that resonance really means, because the reality of it, when we see Lewis structures often drawn, if you're drawing it for a quiz or a test or something that we want you to draw a Lewis structure for, we want to see you draw it this way with the resonance forms, right? But something that happens is that you will often see these resonance structures, sometimes in like textbooks and things like that in particular, drawn something like this, right? We have kind of these dashed lines. So what that's telling you, anytime you have the dashed lines like this, it means that there's resonance that's present there. And it's actually, when you see it drawn this way, a little bit more accurate to kind of what's happening in the molecule. And the reason I say that is if you have one single molecule of ozone, O3, you're never going to see that one molecule have a double bond and a single bond. Instead, you're going to see something that ends up kind of almost more like this, which is that each bond from the central atom to the outer oxygens is going to be between a single bond and a double bond, and more like a bond and a half instead. Because you effectively have one double bond being shared in two different spots kind of at the same time. And so it averages out that each of these bonds are about a bond and a half, but the two bonds are actually equal to each other in terms of like bond lengths and bond strengths and things like that. So you don't actually see an individual single and double bond in the instance of resonance. You see kind of these mixtures, and sometimes, like I said, you'll see like drawings like this that represent what we call a resonance hybrid, which isn't how we normally draw the Lewis structure, but it is a little more representative of what really truly exists for that molecule if you looked at its structure. All right, so that's kind of our introduction then to resonance. We're going to see at least one more example, I think two actually, in the next couple that I'm going to look at on the whiteboards to go through and demonstrate that a little further. But here's the list of compounds we're going to draw Lewis structures for. I'm going to go through the steps for each and every one of these. So to kind of detail our process here, I'm going to leave that there. Hopefully we can kind of see all of these the whole time as I draw these. So the first one I want to draw is going to be for ammonia. Right, so nitrogen being right here in the periodic table, counting across 1, 2, 3, 4, 5 valence electrons. Each hydrogen has 1. So if I want to draw this thing's Lewis structure, go to my drawing software, give me a second here. If I want to draw the Lewis structure then there for NH3, we're going to have a total of 8 valence electrons. And for a skeletal structure, if nitrogen's first, nitrogen's the central atom. Now, for me, connecting all my hydrogens, I already know what this molecule looks like, and I just kind of have a habit of drawing my Lewis structures to kind of match what the three-dimensional geometries and shapes should look like. You do not have to do this. If you draw this Lewis structure with all of your hydrogens evenly spaced around the nitrogen, that is perfectly fine for the Lewis structure as far as I'm concerned. Maybe check with your own individual lecture professors if they're okay with that. I'm okay with that mainly just because when I talk about shapes, that's when I'll talk about geometries and things like that anyway, and we'll have other ways of kind of drawing that as well. That'll be more important to the three-dimensional aspect of what these things look like a little bit later. But for right now, I'm just going to focus on like the way I have it. I'm going to keep the one I have drawn here on the, if I can get rid of all of this. There we go, sorry. I'm going to keep the one that I have drawn here to finish the rest of the Lewis structure. But just kind of our general steps, once I have the skeletal structure put together like this, fill the outer octets, but outer atoms are hydrogen in this case, so I don't actually need to add anything to them. The one bond is all they want. And if I count my total electrons, I've used 6. I started with 8, so nitrogen ends up with a lone pair. And if I want to think of formal charge, right, formal charge for, let's say, the nitrogen, if I want to calculate that real quick for this molecule, that nitrogen has 5 valence electrons normally. It's making 3 bonds. It's got 2 electrons in its lone pairs, so formal charge is 0. Same thing for the hydrogen. If I want to calculate formal charge, every one of them looks the same. 1 valence electron minus 1 bond minus no lone pairs, also 0. So all 0 formal charges. When you have 0 formal charges, you don't have to add anything to the actual drawing itself. That is something I'll show here that the slides, I don't think, did a good job maybe necessarily of showing. For a couple of the examples that we have in a second that do have formal charges, how we actually add those typically to our structures. And same for ions, because we have a couple examples of those here that we'll see as well. So checking last kind of bits then, formal charges were all good here. The nitrogen does have its octet, right? 2 electrons from the lone pair, 6 more here from our bonds, so 8 total. That should be then our final structure for NH3, or ammonia. All right, if we look at the next example then, carbonate. So this one will be a little bit different. So for carbonate, we'll go through our same process. If I look at our valence electrons, again, carbon has 4, oxygen's going to have 6 with where it is in the periodic table. So that means carbon 4 plus, this is going to be 18 from the 3 oxygens, that's 22. But I also have this negative 2 charge, right? And if I have a negative charge, that means I have 2 additional electrons. So I actually have 24 electrons in this structure to work with. For my skeletal structure, carbon's my central atom. So I attach everything to the carbon. And again, I know kind of the actual shape of this molecule at the end, which is why I've drawn this one a little bit differently to start out. That part, not really important to just the Lewis structure aspect of things. Again, that'll kind of come a little bit later. So don't worry about why I drew the starting ones of these differently. You can draw them the same if you'd like. If you're drawing the Lewis structures, that's not a big deal. Now, the next part of my steps for drawing the Lewis structure for my carbonate, fill all my outer octets. So adding all of my dots. Hopefully all of these show up nicely for everyone to be able to see. For all of my oxygens here. So there is all of my octets on the outer oxygens. But now if I count how many electrons I've used, I have 8 on each of my outer oxygens. 8 times 3 is 24. That's all I started with, right? So I don't have any more electrons for a lone pair on carbon. But when I look at that carbon, carbon's not happy yet, right? Carbon only has 2, 4, 6 electrons around it. So if I don't have any electrons for a lone pair, I do have to make a multiple bond. So what does that mean? Well, if I'm going to make a multiple bond, I'm going to choose just the top oxygen for right now to do it to. I take off one of its lone pairs so I can make an extra bond. But now I'm in a situation very similar to the one I had with ozone a moment ago. Right? If I'm looking at this structure, how did I know to make the double bond at the top oxygen and not one of the bottom ones? And the answer is I really don't. And this means that if I could have put the double bond here or here, it's still going to be the same as what I'm looking at now, which means I do have resonance. Right? So a couple things before I draw the resonance structures. I do want to finish kind of the structure of just this particular resonance structure first, and then I'll add the resonance forms. So typically if we have ions, we put those ions in square brackets with the charge on the outside to indicate the overall charge. And the other thing is if I have this overall charge in an ion, that means there has to be formal charges somewhere in my molecule. And the nice thing about formal charge, hopefully now you've seen a handful of examples of it popping up. It's very pattern-based. So oxygen with 2 bonds and 2 lone pairs is 0 formal charge, but an oxygen with 3 lone pairs and 1 bond is always a -1 formal charge. And so both of those oxygens in the bottom have a negative formal charge. And the way we usually indicate this, and this is, I think, pretty much all faculty will probably expect you to show formal charge in Lewis structures if there's a non-zero formal charge. We will usually show this by putting the charge with a little circle around it next to the atom that has the formal charge. So each of these outer oxygens in the bottom have a negative formal charge there. All right. So that would be our complete structure without resonance, but since this molecule also has resonance, right, we can use two-way arrows to kind of show what our other structures look like. But typically for resonance, I know this is how I treat them. Again, you might want to check with your own individual instructors if you're looking at this too. if they want you to, if they're okay with you kind of showing it this way, or if they want all the details on all the resonance forms. But usually for me, I just want to see something like this that is going to show me that there is resonance that's happening. And I don't need more detail than basically what I've put here. So I'm not making you redraw the brackets or the formal charges or some of those pieces. I just want you to show me that, yes, here's the double bond basically moving to the other possible locations, right? And our other option would be this one. And so that would be then my resonance forms that would be possible for carbonate. And you might see a two-way arrow between the two ones that I just drew there. So there would be all our resonance forms. Again, I don't need every bit of detail on the additional resonance forms. I think that basically if you've already drawn all the details on one of them and they're all correct, like then it's just extra time to draw them all again. So as long as you can show, hey, this does have resonance, here's where the double bonds are going, and just put like the lone pairs on the inner and outer atoms, that's usually going to be sufficient to demonstrate resonance for what we're going to see. All right, so that's everything then for carbonate. If we look over here for our next example, I have BF3 as my next one listed. So we'll take a look at BF3. So for BF3, if I want to count my valence electrons, right, boron being right here, 1, 2, 3 valence electrons. Fluorine I've seen a couple times, the halogen is going to have 7 each. So that means my boron is going to have 3 valence electrons, 7 each on each of the 3 fluorines. 7 times 3 is 21, plus 3 is 24. Apologize if you hear talking in the background here from my stepsons. But if I now go to my next step for my skeletal structure, again, I have boron as my central atom. It's the first one listed. So all my fluorines attached to it. I'm going to fill my outer lone pairs. And if I count my number of electrons that uses up, it's going to use all 24 electrons. Right? I have 8 on all 3 of these. So I don't have any electrons left for boron, which means for boron to get an octet, I would have to make a multiple bond. Now, this particular case is going to be kind of maybe different than our normal expected, because there is something that comes up with boron that I think we mentioned as an octet exception in our last lecture, and that's boron's kind of our most common example of an element that's okay with an incomplete octet. This is extremely kind of uncommon. Boron chemistry, we don't see boron pop up in a lot of compounds in general chemistry, mainly because boron honestly is just really weird. It does a whole lot of weird things from kind of a chemical structure standpoint, mainly because it's okay with these incomplete octets a lot of the time. So it makes some really weird cluster compounds. But the big important part here is that boron and other elements in its column, right, if I go back to the periodic table, like aluminum or gallium, aluminum and gallium will sometimes do this too. And indium and thallium down below it don't usually do it as much, but boron in particular does this a lot. Boron will not take a full octet. And the reason it's okay staying just as it's drawn right now is really just formal charge. Right? If I'm calculating formal charge again, let's do it for boron first. Formal charge for the boron has 3 valence electrons minus 3 bonds, no lone pairs. It's a 0 formal charge. Right? For the fluorines in this case, 7 valence electrons minus 1 bond minus 6 electrons in lone pairs. They're also 0 formal charges. If I made a double bond here, this boron would now have 4 bonds and would get a -1 formal charge. The fluorine would, if it made a double bond here, this would go to 2, but this would go to 4, and so it would actually be a +1 formal charge on a fluorine. And if we think about formal charges, these are the charges the elements want. If you think about fluorine, fluorine always wants to be -1, right? Like oxidation states early this semester, it's always -1. Now that we've talked about electronegativity, fluorine's pretty much the most electronegative element in the whole periodic table. Fluorine, there's no way fluorine is going to be okay having a +1 formal charge in the structure that we're drawing here, especially not to give boron a negative formal charge. And so what ends up happening is it stays just exactly as we've drawn it here initially. We leave it with the incomplete octet, and it's perfectly happy that way. Like I said, boron is able to be stable with those incomplete octets because it's able to keep that 0 formal charge. So this is just one indication of kind of the importance of formal charge to a lot of Lewis structures. Now, there are no other elements that we're going to encounter outside of boron and maybe aluminum and gallium that are in that same column. that will do this. So it's not like this is going to happen all the time. It's extremely rare, but it is something that I wanted to kind of highlight here because we saw some expanded octet examples already previously. So I wanted to show one with an incomplete octet here as well. All right. If we move down our line to our next example, then we'll take a look at N2. So for N2, we've seen nitrogen a couple times now, I think, as well. Each nitrogen has 5 electrons, so it's 10 electrons for the whole structure. For a skeletal structure, if we only have 2 atoms, we're just connecting those 2 atoms. But in terms of our general steps, you want to pick one to kind of be the central atom. So in this case, I'll just choose the left nitrogen to be our central atom in terms of our steps, because remember, my next step is filling the outer octets. So I'm going to fill the outer octet on, this is going to be my only outer atom in this case, so I'll fill the octet on this nitrogen. And then if I count how many electrons I've used, there's 8 total here around this nitrogen. I started with 10, so I have 2 left over to be a lone pair on my other nitrogen. Now, the problem with this structure at this point is that if I look at my so-called central nitrogen, it only has 4 total electrons around it, and I don't have any more electrons to add. So that means I do need multiple bonds. So if I want to do that, I need to take off a lone pair on the central, on one of my outer atoms, in this case the right nitrogen, make an additional bond. This gets me to 6 electrons on my left nitrogen, so I actually have to do this process one more time, get rid of an additional lone pair, and I actually end up with a triple bond. And so this is a good example where all of our rules that we've been doing for all of our examples, it still applies even to these small diatomic ones. Just pick one atom to be central and then follow the steps the same way you normally would. And our final structure here, notice nitrogen has 2 electrons in lone pair on each of them, and they each have 3 bonds. If we think about formal charge, we said they each have 5 valence electrons, so 5 minus 2 minus 3 is 0. This is part of why nitrogen gas is extremely stable. Triple bonds are very strong. And this is why a big reason why nitrogen makes up such a huge percentage of our atmosphere and the air that we breathe. All right, one last example, and then I'll move into some things with bond energies to kind of wrap up. So for sulfate, SO4 2-, this one's going to be a little different. And I really want to show this example because it does something that's kind of strange compared to what you would normally expect. And this one is going to have a whole lot of resonance because of what it does. In fact, I probably won't even draw out every single resonance structure. I'll kind of demonstrate how we get to each of them, which is fine. But I am going to show just in general, like this thing is going to have a lot of resonance in it. And I'm going to explain, hopefully, with some good reasoning why that happens. But to just go through our normal steps, sulfur is right below oxygen in the periodic table, so all of these have 6 valence electrons. So 5 times 6 is 30, plus 2 additional ones is going to be 32. So I have 32 electrons to work with in my structure. From a skeletal structure standpoint, sulfur is going to be my central atom. All right, I connect all my oxygens. And this is not the actual 3-dimensional shape this time. This is going to be a little different. I just think it's going to be easier for me to draw things this way for this one. So when we go to add all of our outer octets, if we count how many total that's going to end up using, if I have 4 octets, 4 times 8 is 32. Well, I started with 32, so that means no lone pairs in the sulfur. Right? So I get to this for my structure, and I look at it, the sulfur has an octet, all the outer oxygens have octets, so that should be it, right? Everything's happy. But this is not actually the best structure for sulfate, right? I can add the other piece here. This thing should have its brackets for its -2 charge because it is an ion, which means if I have a -2 overall charge, there's formal charges somewhere in here as well. And if I look at each of these oxygens, notice none of them are the normal two bonds and 2 lone pairs of electrons that we're used to seeing. They're all 1 bond and 3 lone pairs, which means every one of these oxygens right now has a 0 formal charge. And if all of those have negative formal charges, for my total charge of the ion to be -2, that means this sulfur actually has to have a +2 formal charge. And in general, +2 formal charges are extremely unstable. And so that's kind of what ends up happening here, and part of why this thing kind of rearranges a little bit. is that we want to get rid of these formal charges. Right? Our goal is to minimize formal charge, and there is a way to actually do this in this case. Sulfur is in the third row of the periodic table, which means that it can expand its octet. And so we can actually expand sulfur's octet in this case. I'm going to do that. Let's do that for the right oxygen and the top oxygen. And let me orient this the way I normally would for putting this together. We can rearrange it to make 2 double bonds instead. Lost my central sulfur. And by doing that, what I've done is I got rid of the +2 formal charge on the sulfur and the negative formal charges on the oxygens, right? Because now each of these oxygens has 2 bonds and 2 lone pairs. That's what they normally like. Sulfur has 6 valence electrons, making 6 bonds. That's now a 0 formal charge for it also. So this is a better structure than the first one that I drew because it has has fewer total formal charges. The one tricky part about this one is the fact that if I'm looking at this, I now have 2 double bonds that I drew here. How do I know to make the double bonds here and here and not like here and here or here and here? And that's the answer that we don't, right? This thing has a lot of resonance, right? In fact, it has, I believe, 6 resonance structures because I could have the 2 double bonds where I've drawn them here, or I could have the double bonds here and here, or here and here. There would be 3. I could have the double bond here and here, it would be 4, here and here would be 5, or here and here would be 6. So there's 6 different combinations of where I can put those double bonds. I'm not going to draw them all here out just to show all the resonance forms. It's probably unlikely to make you draw out all of those in something like a test, unless it was like a pretty significant point question just to have you show us all those things. But it is something to kind of keep in mind. There is a lot of resonance forms that are present here. And again, it comes because all of these outer atoms are the same, and I was making extra multiple bonds to my central atom, so I don't know where those necessarily are going to go because they're all equal, and that's what gives us this resonance. And the resonance actually, even though it seems kind of very strange, the resonance helps stabilize things quite a bit. And so resonance actually helps stabilize molecules so that they are more stable than you'd maybe normally expect. And that's something that will kind of be a continuing factor that pops up in a lot of things in the future, both in 1212 and in organic chemistry as well. The last thing I'll note here, as far as kind of putting everything in for our resonance, because there is resonance here, that means there's no single and double bonds in reality. Really, it means each of these, since I have 2 double bonds being shared across kind of 4 locations, all of these are really about a bond and a half. So all the bonds are equal in this structure, which is something else I want to point out. And it used to be one of the questions I think that was in our lab that we used to ask. I don't remember if it's one that still pops up in our post lab there or not, but kind of something else to keep in mind there. All right, so I think that's plenty of hopefully Lewis structure examples for right now. We'll probably have some additional ones that we'll look at a little bit towards the end of the week. But I am going to also go through and kind of finish up the last couple slides that I wanted to talk about here. So the last couple slides are going to move in a slightly different direction here. We're going to talk about actually bond dissociation energies. And so really the purpose, sorry about that, the purpose of our bond dissociation energies in this aspect, I mentioned them a little bit before in a previous lecture, but we actually want to apply them to calculating enthalpy change for a reaction, right? The stronger our bonds get, the higher the enthalpies, basically the bond dissociation energies are going to be. So like a hydrogen-fluorine bond is actually quite strong, right? Because they're both really tiny, and so they're able to get very close. It's a pretty strong attraction. So it has a really big bond energy. Double and triple bonds are stronger than normal single bonds, right? Here's a CO single bond, 350, CO double bond, 732, so much stronger. And notice they're not exact multiples either. So just because something's a double bond, that doesn't mean you take the single bond energy and multiply it by 2. If something's a double bond, you use the double bond energy. And the main application of that, in terms of where that's actually going to show up or where that's going to be used, is what I have in this next slide, which is finding enthalpy change from bond dissociation energies. So we can calculate enthalpy change from bond dissociation energies, and the way that we actually do this is we can take the sum of all of, oops, this actually should say, let me fix this. I apologize for having to do this in the middle of the lecture to fix this slide. This probably shouldn't say enthalpies of formation. Apologize for that part. Should just be the sum of all of our reactant bonds minus the sum of all of our product bonds. It's going to look very similar to the enthalpy of formations that we used previously, but it's actually the opposite order, right? The reason for this is those bond dissociation energies, that's the energy it takes to break the bonds. And if we think about our chemical reaction, in a chemical reaction, we break the reactant bonds. So those stay like the normal sign for delta H if we're adding up basically everything that's happening. But for our products, those are going to, any bonds present in our products, those are bonds that we're forming. And if we're forming a bond, instead of taking up that much energy to break a bond, you actually get that much energy back instead. It's just right like a normal delta H interaction. If we reverse the reaction, it reverses reverses the sign. So that's why it's going to be reactants bonds minus product bonds in this case. Also, like the enthalpy of formation examples we saw before, we also are going to pay attention to stoichiometry for these types of problems. And so keep that in mind. I'm going to do a full walkthrough example here in just a second so you can kind of see how this process actually works. And hopefully that will detail things nicely for everyone so that you kind of see what the problems of this type would really entail. But really, it's just an additional way for us to calculate enthalpy change for reactions now that we know a little bit more about molecule structures and Lewis structures. So to take a look at an example, I'm going to take a look at this particular one. Right, so we have 2H2 plus O2 is going to 2H2O. That's our reaction. And I'm going to do this on the whiteboard so you can kind of see everything getting mapped out. So I'm going to leave the reaction hopefully up there where we can see pretty much all of it there. So our reaction is we have 2H2, right, plus O2 going to 2H2O. And what we want to think about is our Lewis structures. Right? For H2, if we draw out its Lewis structure, it's going to look like this. We do have two of them, though, two molecules of H2. So this means we effectively have two hydrogen-hydrogen bonds. Right? That in this reaction we're going to have to break. For O2, if we draw O2's Lewis structure, it turns out, I can go through the steps here as I put it together. Right? We can start with a single bond. I can put outer octets. I'll call the right one the outer atom again. That's actually going to leave us two lone pairs for the other oxygen, but I'm short electrons to give it the octet, so we do actually end up with a double bond. So O2 looks like that. It does have a double bond, which means we have one oxygen-oxygen double bond on the reactant side that we're going to break. And then for our products, we have two waters. Right? Well, we saw water's Lewis structure earlier. Each water has two oxygen-hydrogen single bonds, which means total, I actually have four oxygen-hydrogen single bonds that I'm going to be forming. So how I'm going to calculate delta H is I'm going to use the bond energies that were in the table a couple slides ago. So I'm going to pull up the tables here, and that's where I'm going to pull my numbers from. So if I go back to this table, oops, sorry about that. If I go back to my table here, I'm going to look for hydrogen-hydrogen bond is 436. So back here in my problem, I'm going to have 2 times 436, right? Reactants first. And then I have an oxygen-oxygen double bond, which from the table, oxygen-oxygen double bond is 498. So plus 498 times, put times 1 here, because there's the 1 O2. There's all my reactants, and then I need to subtract my products, which is going to be 4 times, in this case, hydrogen oxygen is 460. Right? And now if I do the math on this, which actually I'm going to have to take a second to actually think about this and do the math on this myself. So we have oxygen double, okay, it was 498. So I don't have a calculator sitting next to me, so I'm actually doing this, attempting to kind of just quickly do this in my head. Let's see. 60. I believe if I can do mental math, which some days I can, some days I can't. I think this comes out to negative 450 kilojoules per mole. But let me actually double check this here and make sure I'm doing this correctly. Oh, I'm sorry, it's not minus 450. Let me fix that. Apparently I cannot do my mental math today. So apologies for my little delay here. So I believe it's actually negative 470. Sorry. And I'll do one more last check just to make sure that I'm not crazy and losing my mind here, since I've been kind of recording this here for a bit. So one last check. Yes, negative 470. Okay. Sorry for the little delay there, but hopefully it gives people kind of time to maybe catch up and check the math on your own as well. So negative 470 kilojoules per mole, those are kind of the units here that we're actually looking at for everything, right? Units and all of these were kilojoules per mole for all those interactions. If you wanted, you could maybe say kilojoules and say like this is the moles for the units. Really just depends on whether they're asking for units of kilojoules per mole or kilojoules for the delta H. Kilojoules per mole are probably a little more common, and so that's what I'm going to go with here for writing out the units. All right, so that's the last example problem that I'm going to kind of walk through for this lecture. I think it's already kind of gone fairly long. I apologize for that. For the next lecture that I'm going to go through, I'll probably come back and do maybe one more example of this type, and then I'll talk a lot about kind of just electron geometries and shapes. And then also we're going to spend a lot of time just looking at examples of drawing Lewis structures, getting the actual VSEPR geometries, and kind of hopefully just getting used to that process. Because like I said, we go over it a lot in lab and lecture because it is a really important topic. So that's what'll be coming up for the next couple lectures here as well. All right, if anyone has any questions, feel free to send out an email, let me know. Otherwise, I will see everyone next time.